I'm gonna record this session. Thank you for reminding me, Wesley. So I was explaining this. We were looking at the a probability distribution. We found the expected value, which was called the mean value, the mean. And also we were able to find the standard deviation and the variance. So why do we want to do that? So we want to do that because so we want to see the underlying distribution and how much variation we might expect from this distribution. So so we also went through the idea of the permutation, first the factorial, then the permutation. We are using factorials. I also showed you how to do it in Excel. So I didn't spend way too much time on this because this is just a computation that we need to use. So tonight, I will be ending the class by 7 o'clock, no 7, from 6:15 to 7. Yeah, but a little bit around 7:10. So today is the presidential debate that I will never miss, or I will not miss for anything. So I'm very interested in this presidential debate. So so I probably will end the class a few minutes before, but that's not very likely. So also I want to say we have how many more classes before the next test? So we have class today. So we have class tomorrow, and we have 2 more classes before the exam. So so the exam, sapling and the exam sapling and the Excel file are going to be due by October 11th. So we have plenty of time to do all these assignments. So I just want to make sure. I'm going to be sending reminders later today. So we meet today, we meet tomorrow, we meet Monday and Wednesday, and then the following Friday, the following Sunday is going to be the deadline for all the work. Okay. So so we are familiar with the binomial distribution. So remember, the binomial distribution it comes from the binomial experiment. So in the binomial experiment, you have only 2 choices: the probability of success that we are going to call P, and the probability of failure that we usually call Q. In some cases, P it's always P in most of the literature, and Q is 1 minus P. So it's exactly the same. So in many books, instead of seeing like, for example, P times Q, you're going to see P times 1 minus P. So so this binomial experiment has 3 different characteristics. So there are fixed number of trials. So think of a trial as the repetition of an experiment. So the letter N is gonna call for the number of trials. So in many cases, and we have been talking about this, N represents the sample size. So in this case, the sample size is the number of times the trial is repeated. So we have only 2 possible outcomes. As I mentioned before, you can have the probability of success and the probability of failure. So the letter P denotes the probability of success on 1 trial, and Q denotes the probability of failure. So if we add success and failure, we are going to get the 100% of this experiment, right? So so and the N trials are independent. So that means that these probabilities are not going to change. So so those trials are independent, and they are repeated using identical conditions. So because N trials are independent, the outcome of 1 trial does not help predict the outcome of another trial. But so what is true is that we are going to be using these numbers. So sorry. So we are going to be using the trials as independent events. So that means that the outcome of the second doesn't affect the first, right? So that means basically that the probability is going to be always the same. So, so the outcome of a binomial experiment fit what is called a binomial distribution. So the random variable X, for example, the number of successes obtained in any independent trials is going to represent this binomial probability distribution. So based on this, we can find the probability of an event, so given certain conditions. So, and based on this information, we can find the mean, the variance, and the standard deviation. So I'm going to show you this. I mean, this is very simple. If you did the exercise last time, like the table I showed you, so you probably figured that out. So we have a binomial probability distribution that is attached or is related to this binomial experiment. So, and we can find the mean and the variance, and of course, the standard deviation. So for this probability. So in order to find the mean, we're going to multiply the sample size, so the number of times the trial is repeated, times the probability of success. So, so keep that in mind, because in some cases we have binomial distributions, so we can use these. So at the end of the chapter, you can see that in some cases you might say, what should I use? Should I use a binomial distribution? Should I use a Poisson distribution? Should I use a hypergeometrical distribution? So in many cases, you can do some transformations. So keep that in mind, that in the binomial experiment, when you want to find the mean, you're going to multiply the sample size times the probability of success. And to find the variance, we multiply the sample size times the probability of success times the probability of failure. And of course, if I take the square root of this, I'm going to have what is called the standard deviation, okay? So this standard deviation is a value that we want to find for our computations. So any experiment that has the characteristics 2 and 3, meaning that we have two different outcomes, failure and success, and the trials are independent, they are called, where the sample size is 1, is called the Bernoulli trials. So a binomial experiment takes place in the number of successes is counted more in one or more Bernoulli trials. So the Bernoulli trials implies success and failure, and the trials are independent, so that happens once. So this binomial is when we have, so this idea that we're going to analyze is that when a number of successes is counted one or more in a Bernoulli trial. So so I have this idea. So how do I interpret this thing? So let me so open my so for example, I am interested in finding the the binomial distribution of this. So, well, first of all, so before doing that, so just imagine that we are doing how to say 9 surgeries, and each surgery has a 75% of success. So as I mentioned before, based on these two numbers, so of course, I have the success, I have the failure probability, which is going to be Q. And Q, remember, is 1 minus my probability of success. So I'm going to have this. So let me be consistent with this. I'm going to put some yellow. And so if I want to find the mean, so once again, my my binomial distribution mean is going to be found by multiplying the number of trials times, oops, sorry, the number of trials times my probability of success, right? So this is going to be my mean. So you are going to see what happens with this. The standard deviation is going to be equal to the square root. I have the formula here. So the square root of n, which is 9 times p times q, right? So that's the standard deviation. So let me make it bigger. I guess many students might be not able to see it. View, zoom, I'm gonna put 125. And the reason is I need a space. So we can find these basic statistics. They are gonna be very helpful. So far I haven't answered any question. So what I'm doing is I'm looking at my data. So I have nine surgeries. The probability of success in a surgery is 0.75. The probability of failure is 0.25. So what is the mean value of this? Well, it's gonna be 6.75. And the standard deviation is gonna be 1.3, more or less. So in this case, so we can find also, so the bell shape here is basically, so the variance. So in this case, so because this is the formula of the variance. So here, as I said before, this is m times p times 1 minus p. So this is q. So I'm gonna say equal, n is gonna be 9, once again, times 0.75 times 0.25, right? So this is my bell shape. So so this is basically this is the formula that we know as the variance. Also, we have so you might ask, what are the values that are bounding the two standard deviations to the right and to the left? Well, that's not difficult to find. So we're gonna say that if I so my mean, this is my mean, and then I subtract two standard deviations. So the standard deviation is this, and then I am gonna do the same, but with the positive sign, right? So equal mean minus two standard deviations. Sorry, that should be plus. So let me fix it. So this is gonna be plus. So the second is a plus. Okay. So if you have like for example, in this case, just drawing this map. So I don't know exactly what I'm doing here. I'm not what I'm doing here. But if I have to guess, so let's assume that we have something that looks like this. So we have a potential distribution that looks like this. So just imagine that we are doing something like this. So this is a normal distribution. So I'm gonna have a mean that this is going to be mu is gonna be equal to 6.75. So sigma is gonna be equal to 1.3. So two standard deviations to the right, two standard deviations to the left. So this value, mu minus 2, this value is going to be more or less here, right? So let me make this. So of course, binomial distribution is a discrete distribution. So instead of having this, we're going to have bars, but I'm just sketching the idea. So this can be 0.15, and this point is going to be 9.34. Sorry for the bad, right? Okay, so that's going to be this idea is going to be modified, because remember, my binomial distribution is a discrete distribution. So I'm gonna have bars and everything, right? Something like this. I'll show you how it looks in real life. But what we have to visualize is that we are going to be able to find the mean, the standard deviation, and in this case we can see so whether this any value that is unusual should be lower than 415. Any value that is also unusual to the right has to be greater than 9.34. So we know that from the theorems that we have stated before. So in this case, so how can I solve this? So if somebody asks me, what is the probability that more than 3 are going to be successful? Well, I don't know. So what I can do here is I can build my binomial distribution table. I mean, I can do it. For example, I can use this formula to find this value. But if I want to find more than, less than, at least, or at most, I have to use a normal distribution, a binomial distribution table. So in this case, we have two different things. So we have the probability. What is the probability of 0? I'm going to find it. The probability of 1. So, but also I can find the cumulative probability. What is the probability that more than 4, less than 4, so forth and so on, right? So in this case, we are going to start by finding the probability at that particular point. So this is going to be what I want to do, right? So I can do the following. I can do equal binom that dist. So I'm following this formula. Open parentheses, the number is going to be 5. The trials are going to be 9. So this is the 9. And then the probability is going to be 0.75. And cumulative is going to be false. So why false? Well, I want to know what is the probability of 5, right? So, so I can do this very easily. So I can compute all these probabilities and even graph it. So I will be able to solve these questions, right? So in this case, I'm going to do the binomial that dist. So this is going to be the number, comma. This is going to be the number of trials. I'm going to put a $sign, comma. It's asking me for the probability. It's going to be, this is the probability. I'm going to put also a $sign. And then the last one is going to be the cumulative. I'm going to say false. I'm going to say false, right? So just follow this. So here we have a probability that is very low. So let me put it in numbers. I'm going to add some zeros. So you can see that the probability is very low. I'm adding zeros here. So I'm going to pull this and drag this down. So so let me see. It should be 1, right? So in order to see whether I'm doing the right thing, so my point is here. So I am a surgeon. I am or I am a patient, and there are 9 surgeries. I am one of these surgeries. I don't know what number is this, but I want to know what is the probability that my surgery is going to be successful or not successful. So we have some probabilities attached to this. So so in this case, my point is I was looking for the probability of 5, right? So the probability of 5 is exactly the one that I computed here. So here I am using the Excel function. So the question is also, what are the values that my random variable is gonna take? So for example, in this case, is there any probability that 0 are gonna be successful? 1, 2, 3, 4, 5. So so that is the point. So here, so if somebody asks me what is the probability of more than 3, so more than 3, remember, so if I have to say more than 3, So that's going to be equal to how many? So it's going to be 4, 5, 6, 7, and 8, and 9, right? So that's what I have to do in order to find what is the probability that more than 3 are going to be successful. So what I'm going to do here is I'm going to sum these 4, 5, 6, 7, 8, and 9. Proof equal sum. So greater than 3 is going to be 4, 5, 6, 7, 8, 9, right? So the probability that having more than 3 surgeries right is 99. So it's kind of like very high, of course. So the probability of less than 7. So remember, less than 7 is going to be equal to 6, 5, 4, 3, 2, 1, and 0. Right? So I'm going to do the following: less than 5, less than 7. So it's going to be the sum of less than 6. Sorry. So if I want to find the at least 5, so at least 5 means 5, 6, 7, 8, 9. Okay. So at least 5 includes the 5. So I'm going to do equal 5, 6, 7, 8, 9. Okay. So I made a mistake. The sum of okay, and then at most 5. So at most 5 is going to be equal to 5, 4, 3, 2, 1, and 0, right? So I can find these probabilities very easily. So equal. So at most 5 is 5. No, right? What happened to me? That has to be equal to the sum of 5, 4, 3, 2. Okay, something happens. Doesn't let me the sum. Okay, it's taking a little time, but that's so I saw this. So this cumulative basically is going to be adding all these numbers, right? So if you want to know, for example, I'm going to use the second formula that has, instead of the false, has the truth, the true. So I'm going to find the binom that is, this is my number. So the trials are going to be 9. I'm going to type the numbers. I think it's going to be the probability 0.75, and this is going to be true, right? So as you can see, this number and this number are exactly the same, right? So, so what we can say is that, so if I drag this down, what I'm going to see here at the end is 1. So this cumulative is going to be adding all the numbers down. So the second one is going to be the addition of the first of 0 and 1. This number is going to be the addition of 0, 1, and 2, so forth and so on. So at the end, we have a 1 at the end, right? So probably I'm using so many zeros just to show that this is, so these numbers that look like 0 have indeed a number, right? So we can do the cumulative, for example, less than 7. Well, more, so less than 7. So we have from 6 so the cumulative number, as you can see, is equal to this. So so we can use this table to compute some of these values. Okay, so I also said we can graph these numbers. So so in this case, when I presented that a sketch of the diagram, so I can do it the way it should be. So we have a column bar. So this is going to be my distribution based on, so this is my histogram. But remember, histograms have the bars next to each other. So we have to get rid of the gap. As I mentioned before, don't use the histogram that comes with this. So as you can see, if you see here insert, you have a histogram. That doesn't help too much. And I don't know what happened with this graph. I guess it's broken. Now it's not broken. So as we can see, so this is my distribution based on the probability distribution. So we have a mean value that was equal to how much? So let me take that value from here. So we have a value that is 6.75, and we have a standard deviation that is going to be equal to this point, right? So let me erase some of the zeros. So this is sigma, right? And sigma is going to be, so we have the distribution. So you can do it by hand, and you can use this formula. So I don't recommend it because, well, I mean, you can do it if you want, but if you are doing your exercises in sapling learning, it's very easy to do it using the table. Okay. So as we can see, we have the mean value. If I can draw something here, so my mean is going to be more or less like here, right? 675, very close to 7, where we have the highest bar. And sigma is going to be 1.3. Okay, so that is very helpful. So so we can do that. So we have some other exercises here. So I was taking this information from table slide number 17. So far we have the binomial distribution. We were able to compute the mean and the standard deviation and the variance. So so let me go to this. So this is the notation for the binomial. So the probability distribution, this binomial probability distribution function. So this is like, for example, it says that the random variable x follows a binomial distributions with parameters n and p, n being the number of trials, the sample size, and p being the probability. So that's basically what we need to solve our case, but among other things, right? So, but those are the things that we need to know to begin with. So my binomial distribution is going to depend basically in these two parameters. So this is an example. It has been stated that about 41% of the workers, so this is very important, 41% have a high school diploma. So that is going to be the probability of success, but they do not pursue any further education. If 20 adults are randomly selected, find the probability that at most 12 of them have a high school diploma, but do not pursue any further education. So how many workers do you expect to have a high school diploma, but do not pursue higher education? So, so let X be the number of workers who have a high school diploma, but do not pursue any further education. So my random variable is going to take values from 0 to 20, because here I'm finding a sample of 20 adults. And so that is the sample size. The probability is going to be 41. Of course, Q is going to be 1 minus 41. So, and the random variable is that at most 12 workers, right? So what I'm gonna do here is I'm gonna reproduce this case. So for example, as I said before, we need an N, which is the sample size in this case. So in this case, the sample size is gonna be 20. So it's gonna be 20. N is gonna be 20. So the probability of success is gonna be equal to 41.41. And the probability of failure, Q, is gonna be equal to 1 minus the probability of success. And we also need the random variable, right? So in this case, the random variable is gonna adopt values from 0 to 20, right? So 20, because that's the sample size. So I'm gonna build this for 20 people. So so here I'm gonna find the probability, this binomial probability attached to these values, right? So the goal is to find, so the probability that X is at most is equal or less than 20, right? So at most means that it's equal or less than 20. So it's gonna be 19 to 0, right? So, no, sorry, 12. So this is at most 12. So I was kind of getting confused. So the goal is to prove what is the probability that at least or at most 12 of them have a high school diploma and they do not pursue any further education. So I'm gonna use my formula. So I'm gonna say equal binom that is, open parentheses, this is my number. We have trials that are 20. I'm gonna type the number because I think it's easier. So, and I am gonna say the probability is 0.41. So what I'm doing is I am avoiding putting all these dollar signs and stuff. So in this case, when I use dollar signs, is more is easier, because what if I change the probabilities? So I realize that I made a mistake, so I have to change all of them. So in this case, I want to find this probability that 0 workers are going to have a high school diploma and they are not pursuing higher education. So, and then I'm going to say false. So remember, the false gives you the probability of 0, the binomial probability attached to 0. So that's the first value. So I'm going to go this this way. So this number should be equal to 1. So so this is equal to 1. So that means we did the right thing. So we choose the right random variables and the right number of well, we chose the right parameters. So in this case, once again, this is based on a 20 a sample of 20 adults. I want to know what is the probability that at most 12 of them have a high school diploma. So once I found these values and I determined that at most means 12 and less, so I'm gonna say the summatory of 12 or less. So so 12 is not included, and most, yes, 12 is included, sorry. 12 is included. So what is that probability? Well, it's 97.3%. So so how many adults do you expect to have a high school diploma but do not expect to pursue further education? So so this is the probability that we find that is attached to less or equal to 12. Okay, so let me put some little, especially this, because those are data that we are including. Okay, so so that's how we can use this idea. So the formula for the binomial distribution, so is the factorial of the sample size. Well, it's kind of so this is a combination that is multiplied by the probability of success times to the power of x. So this is x. So we have to analyze this formula at every single point. So we have the combination of n chooses r. So n is going to be always 20. R is going to be changing all the times that we go down. So this is the probability. Also, in many textbooks, they use pi as the probability. So this is the probability of success elevated to the power of my random variable, and then times the probability of failure to the power of the sample size minus the random variable. So it's kind of like, I don't see any benefit of showing an example of how to do it by hand, because we have this Excel function, this binomial distribution. So we need the number of the random variable. In this case, this is the number of the random variable. We need the number of trials, and we need the probability of success. And then the cumulative, we can do the false for the probability, for the probability at that particular point, or this is for the cumulative for the distribution function. So in this case, we can also, as I said before, we can graph this. This distribution, insert a chart column. So this is going to be something like this. So once again, we have the highest, the tallest bar close to 8. What happened here? Okay. I know. So I'm gonna close the gaps. So now I have my distribution. So I can compute. Here I can compute the mean. We know that the mean is equal to P times Q, P times N times P. So my mean value is 8. So of course we are so we are expecting that the value is going to fall by the highest, by the tallest bar. So my sigma, well, let's say mu equal sigma equal. So I'm going to use the symbols because those are mu and sigma. So this is going to be equal to the square root of my N times my P times my Q, right? So that is my standard deviation. So I have computed those values. So those are going to be important. So so we have some other cases. I was looking at the previous cases. So you probably are going to get something like this, right? So in sapling learning, you are going to get a text and you don't know what to do. So once again, the goal of this, so let me go more to the left. Oh no, I think I was up here. So let me move this here. Somewhere in here. No, I'm gonna leave it here. So what happened is this small screen drives me nuts. So let me move this a little bit to the. Okay. Now I'm happy. I'm gonna move this graph over here. So now I am able to, now I am able to see the other cases, right? So that's what you get basically in your Excel assignment. No, not your Excel, in sampling learning. So you are gonna get something like this, right? So what you need to do is to identify what you need to do, right? Of course, it's not easy at the first time, but we are gonna try our best. So in this case, it says, suppose you play a game that can you can only win or lose. So the probability of the game is 55%. So here is telling you right now that the probability of success is 55%. So you can have cases where they said, well, out of 100 cases, we have 50 that are, so you have to perform the probability. So remember, the probability is the frequency. It's called the relative frequency too. So, and remember, we found this by dividing the frequency by the sample size. So if you have 5 cases out of 100, so that's the 5%, right? So I don't need to tell you that. I think you already know it. So in this case, we are dissecting this case. So suppose that you can win or lose. So the probability of winning is 55%. The probability of losing, of course, is telling you here, but you can also find it by subtracting 1 minus p, right? So it's 45. So each game you play is independent. That is very important to know. So you are playing 20 games. Oh, okay, I have 20 games. So write the function that describes the probability of that you win 15 of the 20s. So of course, we are not going to do that. I'm not interested in that. I just want to know the probability. So if you define X as the number of wins when X takes values from 0 to 20, so that's the sample size. So of course, there is a probability that I win zero of the games, right? And I might be super lucky and I might have the probability to win all of them. So none of them, all of them, or something in between. So the question is, the probability question can be mathematically stated as the probability that X is equal to 15. So here I can do something very simple because it's equal to 15. I'm going to use the binomial, that distribution. I'm going to say the number of trials is 20. Sorry. So the number is 15 because that's the number I am interested. The number of trials is 20 and the probability is 55. Okay, so I'm going to say false. Remember, false gives me the value exactly at 15, right? So that is the probability that in the 15 game, I'm going to win, right? So I can find the mean. We also know that. So I multiply n times p. So that's my mean value. So the variance is going to be equal to n times p times q, right? So, and the standard deviation, because I already found the variance, I just can take the square root of my previous value, right? Okay, so I'm done. I'm gonna take some of the zeros off. I don't like them too much. So, but what is the question was, is equal or greater than 5? That less or equal to 15, at least 15. So then I need to do my graph. So I'm gonna do the probability of X. So I'm gonna put values here from 0 to 20. So in this case, 20 is a popular number. It doesn't mean that it always have to be 20. So 20 is in these cases, in these examples, is very common. So in this case, the binomial, that distribution, number of trials, number is going to be 0. The trials are going to be 20. The probability is going to be 55, and the statement is false, right? So I'm going to do all these things. So that is the value. So the probability that is greater or 15. So I'm going to replace this because that was the value for only 15. So when the value is greater, is at least 15. So I'm going to use the sum of 15 to this, right? So that is 5%. So so what is the probability that I win 15 or more games? Well, it's very little, right? Probably I will win 1 or 2 or 3, I don't know, out of the 20. It depends, like the probability of winning is very high. So so that's going to be the case. So in this case, let me erase so many zeros. Okay. So so also we have this one, which is also very, I mean, it's very simplistic. So I made some room for this. So we have a trainer is teaching a dolphin to do tricks, so that the probability the dolphin successfully performs the trick is 35%. So I have the 35%, I have the 65. What I could have found that by doing 1 minus my probability of success, and then again out of 20 attempts. So you want to know, so how to find that the dolphin succeeds 12 times. So that means that from 0 to 12. So in this case, it's going to be x is going to be defined by a value that is greater or equal to 12. So we can build so we can build the table, and we can solve this case very easily. So I will let you do it. So remember, these are part of the assignments that you need to do in Excel. So so we went through this a few minutes ago. So so that's an explanation of another case. So we have another case, and you can do this if you want. So it's not mandatory, but if you have the time and want to see how, well, get more practice, of course. And I know that there are many assignments in the problem sets. So we have another type of distribution that is called the geometric distribution. So there are 3 main characteristics of this geometric distribution. It's based on a geometric experiment. So there are 1 or more Bernoulli trials with all failures except for the last one. So for example, I am going to apply for my driver's license. So I know that people might get it in the first time. Some people get it in the second. I don't know. So I need to, I am going to say, am I going to be able to get it at least in the third attempt? So, so in theory, so once again, in other words, you keep repeating what you are doing until the first success occurs, right? So then you stop. So in theory, the number of trials could go forever. Nevertheless, but must be at least 1 trial. So the probability of success and the probability of failure is the same for each trial. So if you have, so that means that the events are independent. So, and we know that how to get, if we add the 2 of them is 100%, and in order to find Q, we have 1 minus P. So X is the number of independent trials in the first success, okay? So example, so I have a geometric distribution here. I also added one a link. So this is a YouTube video. So YouTube video is very good. So presents all these choices. So you can solve the problem using the formula. You can solve the problem using the binomial distribution formula, some amendments that we can do, or the geometric distribution is almost the same as the negative binomial. So, so there is also an Excel function that shows the negative binomial. So that's kind of nice to use it, because you need to identify how many failures before the success. So of course, success is going to be always one, but you need to know how many failures. Then, so we will do that. So let me, Dios mío. Okay, so you play a game. Now this moved. So you play a game. So let me do it here. Well, let me do this first. So those are easier. So for example, rolling a die and the probability of getting a 3 on the 6th roll, right? So K is going to be equal to 6, right? I know that I'm going to roll the die 6 times. So my P is going to be, so in a die, what is the probability of 3? So remember, 3 is 1 over 6, right? 3 is only one number in the die. So that's going to be the probability of success. Then the probability of failure is going to be 1 minus my probability of success. I'm going to make it small here. I don't like too many zeros, so I can keep those zeros, right? So so that's the data I need. So in order to solve this geometric distribution, so this random variable follows a geometric distribution following a parameter P. So that is the probability of success of this trial. So so in order to find these values, we have to follow this formula. So the probability of success times the probability of failure raised to the power of K minus 1. So K is the number of, so it's the sample size. It's kind of the sample size here. So we have 6 different possibilities in a die. So in this case, I'm going to use the formula. So P is going to be 17% times, I'm going to use the probability of failure to the power of K. In this case is K minus 1, right? So do I need another parenthesis? I guess yes. Okay. So that's going to be my value, 6%, 6.7%. So that's the probability of getting a 3 in the 6th roll. So I throw the die 6 times, and I am expecting that the 6 is going to be a 3. So we can do it by using the binomial distribution. I need, so in this case, the binomial distribution is going to use, so this is a fixed number, is going to be 1. So the number of trials is going to be K. The probability is going to be the probability of success, and then I'm going to say false. But I don't stop here. I'm going to divide it by K, right? So that's how we obtain that probability using the using the second one. Also, as I mentioned, so we have the probability, the negative binomial. So these 3 values give you the exact same values. So that is the geometric distribution. So so in this case, I can use the negative binomial distribution. So it's gonna ask me for the failures. So if this is one thing, so 5 are gonna be the failures. So 6 is gonna be the success. So the number of failures before I get the success, in this case, because K is 6, is going to be 5, right? So how many times am I going to fail before I get a success? The answer is 5. Then the success is going to be 1. And then the probability is going to be the one that we know, right? So then I'm going to say false. And it should work, okay? So those are the 3 things to find the value of this. So so it's very simple. So here we have another one. I hope you can do it using the 3 cases. So here, so we were looking at this. Did I do it in another one? I think we have another one. Hold on. Oh, that's the last one. So we can do so geometric distribution. We have this. So you play a game with the chance that you can either win or lose. So let me do it here. So you play a game. So let me copy this. So those are the inputs that I need. So so you play a game of chances that you, oh, that's the one that we did, right? Or no? So you can either win or lose. There are no other possibilities. So that is a binomial. You win or you lose. So the probability of losing is 57%, 0.57. The probability of the probability of losing, which in this case is the probability of success. So your probability of losing is 57%. What is the probability that it takes 5 until you lose? So then this is the probability of losing, but actually is the probability of success. So this is 1 minus my probability of success. And then the K, it says K is going to be equal to 5, right? So so what is the probability that takes 5 games until you lose? So then K is going to be so in this case 5 games. So the 6 is going to be lost. So probably that should be 5, right? So so in this case we can use the same formulas. So let me see if I can just copy. So in this case, the probability question is p equal to 5. So then that should be 5, I guess. So let me check in this case. So I can just copy and paste this. Copy. So because I'm copying the formulas, so I'm gonna get the values here, okay? So so this is very convenient. So in this case, so this is very convenient because I copy the formulas. So the formulas are recognizing these values yeah, already predetermined. So it's very nice. So this case is, I guess, is a little bit more interesting. We have more information. So assume that the probability of a defective computer is 2%, right? So we have a 0.02%. So is 1 minus 2%. So components are randomly selected. So find the probability that the first defect is caused by the 7th component tested. So I need to know whether this is the 7th. So how many components you need to test until one is found defective, right? So in this case, so we have, so I'm gonna copy these formulas because the formulas are already there. So what it's gonna recognize is these numbers, right? So in this case, I can do the formulas again. So I can say equal so that is P times Q to the power. So that was the formula, right? Yeah. So P times Q to the power of K minus 1, right? I'm gonna add another thing. So 1.8%. So I can use the equal the so it was the binomial distribution. Yeah, binomial distribution. One is gonna be fixed. So I'm gonna use K, which is gonna be 7. I'm gonna use the probability, which is 2%, and I'm gonna say false. And then, as I said, I'm gonna divide it by K. So, and the last one is the negative binomial. Binomial distribution. So I'm gonna use the number of successes. There are gonna be 6 failures before I get the success. Then success is gonna be the 7th, and then the probability is 2%. Then I'm gonna use the false. Okay. So so we can play with these numbers very easily. So once again, if you are using these formulas, all you need to identify for these cases is the probability of success, probability of failure, and the K. So the K is how many times you have to wait until the first success occurs, okay? So, and this is wrong, that it should be and the fall 6. So is there any question so far? Is there any question? Is this helpful, not helpful?
It is helpful.
Okay, so I think I'm gonna stop. Well, I think I'm gonna continue with this. So also we can find the mean and the standard deviations of this. So all we need for the mean and the standard deviation, for example, in this case, the mean is gonna be given by 1 over P. So 1 over P here is my probability of success. And my standard deviation is going to be equal to the square root of, so remember, we can use Q or 1 minus P. So I can use Q here. So I'm going to use Q that is going to be divided by P, which is going to be a square or raised to the power of 2, right? So that is my standard deviation, okay? So I can do the same with this and find the mean and the standard deviation. So I hope you can use those formulas. They are very helpful. They are really lifesavers. So that's another case that I don't remember exactly where I got it. I think that was the one that I got it here, right? I think is later on. I think, and yeah, I think this is. So if you can, I mean, you already have the answers. So I think I send you with the answers. So that's how we found this case. So this is the probability that the success occurs at 10 and then at 20. So you, and of course, the mean and the standard deviation for the two things is gonna be exactly the same because the mean is 1 Q over P squared, the square root of all of this. So it's gonna be easier to find. So the next thing, and probably with this, I'm gonna say goodbye tonight. And also because I'm very hungry. So I wrote, or I copy and pasted the Excel Excel code that you need to follow for this particular is called the hypergeometric distribution, right? So the code is hypgeom.dist, and then you have to follow the prompts and identify the cases. So let me get you a little bit of background of this. So there are 5 characteristics of the hypergeometric experiment. So you take attempts for 2 different groups. So for example, you have men and women, and you want to form a team. So and let's say, so this case is very interesting because you have 6 women. No, you have hold on. Well, I will go through this exercise because all the data is here. So you have men and women. You want to form a group combining men and women, and you might ask, what is the probability that 1 woman, 2 women, 3 women are going to be part of that team? So you are taking 2 samples from 2 different groups. You are concerned with a group of interest called the first group. So in this case, if you are so you are in the Congress, for example, you have in the Senate, you have 100 people, let's say 30 of them are women, 70% are men. And you want to form a committee with 5 people. And you might be wondering what is the probability that the group is going to be 5 women, 4 women, 3 women, 2, 1, or 0 women, right? So you sample without replacement from the combined groups. For example, you want to choose a softball team from a combined group of 11 men and women. So the team consists in 10 players. So each pick is not independent since sampling is without replacement. So here we are not dealing with what is called the Bernoulli Bernoulli trial. So so each pick is not independent. So if in the softball example, the probability of picking a woman from the first is here 13/24. So we have 13 women and 11 men. So the first pick is going to be 13/24, but then the probability of picking a man is 11/23. So every time you are putting a person, you are not replacing it. So the probabilities are going to be changing, right? So this is not an independent event. So the outcomes of a hypergeometric experiment fits a hypergeometric probability distribution. So the random variable is the number of items from the group of interest. So I think I copy this example. So here is the example. So the probability of having n women, certain number of women, for a 6-member juror from a pool of 8 men and 10 women. So we have a bigger number of women compared to men, right? So here, so we have, I think R is the sample. How did I do this? The number sample is 6. Oh yeah. So this is the number of people that I want in my committee. So this is the group of interest. So I have 10 women. And out of these 10 women, I have a probability, a total sample of 18. So that means I have 8 more men, right? So once again, I want to find what is the probability that, for example, in the 6 persons committee, I'm gonna have 0 women, 1 woman, 2 women, 3 women, or more, right? up to 6, because that's so what is the probability that we are going to have an all-woman committee? Well, probably not very likely. So in this case, we need certain numbers. So we need the sample S means how many women I want in that committee. So I'm going to calculate the probability of having 0. Then I need some other values like the number sample, the population. So all of these are here. So so here in the case is that the the committee has to be made out of 6 people. So this is the number sample. So then the population, I am interested in the number of women. So I'm gonna have 10 women here. And my total is gonna be 18 people. So that's gonna be the number population. So in order to find this, I'm gonna say equal the height geom dot list. So it's asking me for the number. So this is the sample. Then followed by the number of people in the committee, then by the number of women, and then by the total number of people in that group. And then I'm gonna say false. Remember, false gives you the exact probability for this particular number, right? So the probability that there is gonna be 0 women, so we can calculate it. So that's the reason I am using false. And all of them are gonna be false. So there is a 0.1% that no woman is gonna be in my group. So, what did I do? Oh, I see. I use
dollar sign.
so the dollar sign. Thank you. Yes. So that is gonna be dollar sign. Ay, Dios mío. Hold on. I always why you guys don't remind me that I need to make this bigger. I think that will help everybody, including my eyes. So in this case, I'm gonna do dollar sign in the C13, dollar sign in the C14, and dollar sign in the C15, right? Now we are fine. So so we can do this. So here, so we can grab this. So, but basically the question might be, what is the probability that we have 3 women in the group? Well, 36%. Probably an all-woman team is gonna be not very likely, right? Not very likely. I can graph this and find the distribution, the underlying distribution. So that's my hypergeometric distribution. Okay. Something happens here. Okay, so we have the distribution, right? So I don't remember whether we can find the standard deviation, and but we probably will be able to find. So that's the I wrote here the code, so you can copy and paste it and well, or just type it. So you are going to be prompting the data that you need. So I'm going to stop here. It's 7:30. The debate is getting too close, and I am kind of like very interested in watching what's going on. So do you guys have any question?
Yeah, Professor.
Yes, Daniel?
Hey, how you doing, Professor? It's not on here. I sent you an email, but I didn't get a response. That's all my question is.
Oh, I think I responded to you. You said that you were gonna send me an email last class?
Yeah. No, not the, it's another email after that.
Okay, so I'm gonna look for your email. Thank you for the reminder. Thank you. Yes. So anybody else? Any question? No questions? Okay, so let me stop. Hold on. Let me stop the